Now, today we will discuss about the what of reaction isotherm. Now, student, in the last lecture, we have discussed about so many things about the its free energy, Helmholtz work functions, and the variation of free energy with the temperature and pressure. Now, today we will discuss about the what of reaction isotherm. From the variation of free energy with temperature and pressure, we know that dG, that is the change in free energy, is equal to VdP minus SdT. Suppose this is equation number 1. And if we apply one of the condition for this equation, that is at constant temperature, the term minus SdT becomes 0. And therefore, equation 1 becomes dG is equal to VdP at constant temperature. And suppose this is equation number 2. If we rearrange this equation and if we apply this equation for ideal gas, then instead of V, we know that for ideal gas, it must follow PV is equal to RT. And therefore, instead of V, we can write RT by P. And therefore, this equation 2 becomes dG is equal to RT dP by P. Suppose if we integrate this equation within some limits, that is integration of dG is equal to RT, R and T both are constant and therefore they are kept outside the integration. Integration of dP upon P. Integration limits for this is when the partial pressure is a standard pressure, that is 1 atmospheric pressure. Then suppose the free energy in its standard state for I constituents, then it is equal to GI 0. And suppose the upper limit is the partial pressure is any pressure Pi, and suppose the corresponding free energy is suppose GI. If we integrate this equation within these two limits, then we know that integration of dG is G within the limit GI 0 to GI, and therefore upper limit minus upper limit, and therefore GI minus GI 0 is equal to RT, and integration of dP upon P is ln P within the limit 1 atmospheric pressure to Pi, and therefore it is equal to RT ln Pi. If we rearrange this equation, then this equation becomes GI is equal to GI 0 plus RT ln Pi. Suppose this is equation number 3. We will stop here derivation, and now let us consider a general gaseous reaction. A plus B equilibrium with C plus D. And suppose small a are the number of moles of A, small b are the number of moles of B, small c are the number of moles of C, and small d are the number of moles of D. Then this chemical equation becomes small a into A plus small b into B equilibrium at constant temperature T, C number of moles of C constituents plus D number of moles of D constituents. And if you want to find out the change in free energy for this reaction, then we know that the change in free energy is nothing but the difference between the free energy of all sum of the free energy of all the product minus the sum of free energy of all the reactants. And therefore, change in free energy delta G is equal to free energy of C plus free energy of D for mole C and D respectively. This is the sum of free energy of product minus free energy of A plus free energy of B for mole A and B. It is the sum of free energy of the reactant. Then difference between these two sum of free energy, we get the change in free energy of the reaction. Now, from equation 3, we can write the equation for the free energy of each constituents for their respective number of moles. That is, respective number of moles for capital A is small p, for capital B it is small p, for capital C it is a small c, and for capital D it is a small d. And therefore, AGA is equal to AGA0 plus ART-ln-PA. Like this, we can write the free energy equation for B, C, and D for their respective number of moles B, C, and D. And if we substitute these values of free energy for A, B, C, and D in the equation 4, then this equation 4 becomes like this. That is, delta G is equal to C BC0 plus C RT-ln PC plus D GD0 plus D RT-ln PD and minus in another bracket AGA0 plus ART-ln PA plus DGB0 plus DRT-ln PB. And if we rearrange this term, if we observe this equation, then there are some terms which are in the standard conditions. And therefore, if we collect all these standard terms in one of the bracket, that is, delta G is equal to, in one of the bracket, C GC0 plus D GD0 minus A GA0 plus B GB0 in this bracket plus C RT-ln PC plus D RT-ln PD, it is one of the bracket, minus in another bracket A RT-ln PA plus B RT-ln PB. If we observe the first bracket of this equation, then this is the change in free energy of this chemical reaction in its standard state. And therefore, instead of first bracket, we can write delta G0. And if we write delta G0 instead of that bracket, then that equation becomes delta G is equal to delta G0 plus RT in bracket. If we take RT is common, then we can write this equation like this. And we know that A and B is nothing but ln B to the power A. And if we arrange this equation in terms of these, then we get this type of equation. And also we know that ln A plus ln B is nothing but ln A into B. And therefore, this equation becomes delta G is equal to delta G0 plus RT ln into PC to the power small c into PD to the power small d to the PA to the power small a into P to the power small p. Suppose this is equation number 5. If we apply the equilibrium condition for this equation and constant temperature, then we know that at constant temperature and at equilibrium condition, the value of change in free energy is equal to 0. That is, delta G is equal to 0. And the bracket in the equation 5, if we apply equilibrium condition, then the ratio of concentration of the product to the concentration of the reactant, it becomes constant at equilibrium condition. And therefore, instead of this bracket, we can use another term, that is suppose Kp, where Kp is known as equilibrium constant. And therefore, at equilibrium, if you substitute the value of delta G equal to 0, and instead of this bracket, if we keep the value equal to Kp, then the above equation becomes 0 is equal to delta G0 plus RT ln Kp. If you rearrange this equation, then this equation becomes delta G0 is equal to minus RT ln Kp. Suppose this is equation number 6, where Kp is equal to ratio of product of concentration of the product to the product of concentration of the reactants. And if we convert this ln into the octave base k, then above equation 6 becomes delta G0 is equal to minus 2.303 RT log Kp. Suppose this is equation number 7. Then above equation number 6 and 7, both are known as Vant of isotherm or Vant of reaction isotherm. And if we substitute this value of equation number 6 into 5, that is the condition other than equilibrium, then this equation value becomes delta G is equal to minus RT ln Kp plus RT ln ratio of product of concentration of the reactant to the product of concentration of the reactant. We know that the isotherm is nothing but it is an equation or it is a graph which is obtained at constant temperature. And therefore, equation number 6 and 7 both are known as Vant of reaction isotherm or Vant of isotherm. Okay, got it? Okay, thank you.